Hey everybody, Dr. Retzek here with you. This is our first video in 15.7. You actually have no suggested problems yet, so this video is going to focus on the ideas behind 15.7 and less on doing examples. Our second video in 15.7 will feel a little more concrete and will allow us to practice examples together. Let's get started. 15.7 is about building an analogy to doing double integrals in polar for the case where we're doing triple integrals. Now, I've prepped a few pages of this note already because the drawings are somewhat involved, and we're going to fill in some details on these drawings. So in the olden days, that is, last week, we were trying to do double integrals in polar, and we recognize that there are certain regions, like this region here, that are better described in terms of polar coordinates than they are in terms of rectangular coordinates. And so we thought about how to break up regions like that into little tiny pieces by finely partitioning the angles involved and finely partitioning the radii involved. And any particular such region looks kind of like this thing we're calling dA. And you can see that dA isn't quite a rectangle, but it's almost a rectangle. And if it were a rectangle, then its little area contribution would just be, base times height or width times length or whatever you want to call the dimensions of that little red patch. And you can see on that little red patch, this dimension, well, that's part of a circle of radius r, distance to the origin, and angle tiny change in theta. So that dimension right there is r times tiny change in theta. And then the other dimension, this dimension here, that's a tiny change in radius. And so the dA is roughly, not exactly, because it's not exactly a rectangle, that little patch, but it's roughly r dr d theta, where that squiggly equal sign becomes a better and better approximation as you put more and more little patches in. And to tell the full truth here, we would be doing limits of Riemann sums. And in the end, it turns out that if you're trying to do an integral with respect to area, the moral is, in x's and y's, dA is literally rectangles. So dx, dy. If you're trying to do area integration with respect to polar, then the role of dA is played by r dr d theta. Okay, this is old news to us. We want to generate morals like this one and pictures like this one, but in 3D. And there are actually two different coordinate systems you might elect to use. And so we need to go through each of them and discover the corresponding moral for each of those coordinate systems in 3D. So the question becomes, is there an analogy in 3D? This video aims to get at that analogy. Okay, clean sheet. Suppose you had some region in 3D. That's that amorphous blob that I tried to draw. You can call that region E if you want. If you wish to break E up with X's, Y's, and Z's, go ahead. And that would be like breaking it up into a gazillion little sub-boxes. But maybe the shape of E doesn't lend itself to those really rectangular sub-boxes, and maybe it makes more sense to break E up in a different way. Cylindrical coordinates offers one such different way. So cylindrical goes like this. All you do is you break it up into these little wedge pieces where you keep Z. So the vertical coordinate is still described with Z. So this little edge right here, this is definitely delta Z. And the little volume that's generated, the area of the base of that wedge, there you're projecting straight down into the XY plane, and you have a little polar wedge. So you steal the area that you already understand in polar flat in the XY plane and use that as the base of your wedge. And then the height is still just given by Z. So the height is some small change in Z. And therefore, the dV that we should use, if we wish to describe things by trading in X and Y for polar and keeping Z, that's called cylindrical. Trade X and Y in for polar, keep Z. If you wish to describe things in cylindrical, then that little dV piece of that solid region E, well, it's area of the base times the height, and so we get dz r dr d theta. Again, that squiggly equals sign, it's not exactly a cube with those dimensions, but almost. And as we divide E into more and more such little wedges, and we take a limit and we do a Riemann sum carefully, then the triple integral done dV, you can express dV in this new coordinate system as dz r dr d theta. So the moral when you're doing cylindrical is that the old role of dV was dx, dy, dz. Here, if you wish to switch and trade x and y in for the old polar version of x and y and then keep the z, then you get dz r dr d theta. So that's the moral. When you're switching into cylindrical coordinates, then all you pick up is that little extra r again, just like you did in double integrals when you switched into polar. Okay, but cylindrical is not the only coordinate system that we might want to use to do hard integrals in 3D. So there's another option. This is called spherical coordinates. So let's look at this picture first. Every point in 3D space, like this one here, you could describe explicitly by telling its x, y, and z coordinates. How far out of the screen, how far to the right, and how far up. That's our classic Cartesian description of that point. But you could describe it in a totally different way if you felt like it. That black dot is uniquely described by saying how far it is from the origin. That's that orange Greek letter rho. By saying how far tipped down from the positive z-axis it is. That's that angle, Greek letter phi in green. And by saying how far swung around its shadow down here in the xy plane is from the positive x-axis. And that's our good old variable theta. So in that sense, that black dot has a unique description, rho, comma, phi, comma, theta, that tells you where that black dot is. If you view 3D space through those goggles, where you no longer even see x's, y's, and z's, all you see is rhos, phis, and thetas, you can still do triple integrals in that new variable system with respect to all those new letters. It's no longer dx, dy, dz. It's going to be something with d rho, d phi, d theta. We aim to discover that something. Okay, this picture is kind of tricky, but it's also kind of cool. Okay, here we go. So you have an amorphous blob in 3D space, just like before. You can call it E. So we're interested in doing the triple integral over the region E. And we are going to break E up not into little boxes with dx, dy, dz dimensions, and not into little cylindrical wedges, as we did a moment ago in our discussion of cylindrical coordinates, but rather into these little spherical wedges. So I've tried to draw a spherical wedge. That spherical wedge comes from some tiny change in swing down angle from the z-axis, so some tiny change in angle phi. It comes from some change in distance to the origin, so some tiny change in distance rho. And it comes from some change in swing angle down there in the xy plane, so some tiny change in theta. And we would like to produce an estimate for the tiny volume contribution of that one wedge. Now, I've highlighted in blue the 3 dimensions of that wedge, treating it as though it were roughly a rectangular box. We know it isn't, but that's why we have the squiggly equal sign. We need to identify those 3 dimensions of that one wedge to figure out who's playing the role of dV. Okay, here we go. This one first. That dimension there comes from a change in distance to the origin. So that is a change in variable rho. This one here, this comes from fixed distance to the origin, but change in swing down angle from the positive z-axis. So this is fixed rho and tiny change in phi. And that edge is part of a circle. Therefore, that little edge, that is roughly rho times change in phi. Because that's the arc length along the edge of a circle of radius rho with angle tiny amount of phi. Okay, now this last one, this last dimension, so this one here, that dimension, that comes from fixed rho, fixed swing down angle, so fixed phi, and a tiny little amount of change in theta. So you're imagining this theta changing by some delta theta. And so this distance has to do with how far you are from the origin, flat in the xy plane, and that tiny change in theta. Now, how far are you from the origin? Okay, well, it's this distance from the origin. And that distance is the base of a triangle, where it's a right triangle protruding up, out of the xy plane. The hypotenuse of that triangle is rho. This is swing down angle phi. So that's phi. So that base of that triangle, flat in the xy plane, is rho sine phi. And therefore, this little dimension here is that radius, that distance to the origin flat in the xy plane, times tiny angle change delta theta. So this distance is rho sine phi delta theta. So the three edges on that spherical wedge are delta rho, rho delta phi, and rho sine phi delta theta. So the volume of that little wedge is well approximated by the product of those, and all told, you find out dV is roughly, let's see, rho squared, we got a couple rows, this and this multiply together. We got a sine phi, and then we got d rho d phi d theta. D rho d phi d theta. Thus, the moral, when you're trying to do a triple integral with respect to volume dV, and you're going to go from Cartesian to spherical, well, in Cartesian it's easy. It's dx, dy, dz in any of the 6 orders. We just discovered that if you switch to spherical, the role of dV becomes rho squared sine phi d rho d phi d theta. So that's the analogous moral when you're switching into spherical. And what you want to internalize in all of these, independent of the derivations of where the formulas come from, these are all just geometric things that are very hand-wavy at this moment. What you want to really internalize is this. When you change variables, there is some cost, there is some multiplying factor that you have to keep track of. And in the olden days, when we switched from Cartesian to polar in 2D, the cost was the additional r, and you got to be the pirate. R dr d theta. Here in triple integrals, if you switch from Cartesian to cylindrical, the cost is r again. And you're still sort of a pirate, only you have to say dz. dz r dr d theta. And if you switch from Cartesian to spherical, there is a cost. The analogy to r is rho squared sine phi, and there is no pirate joke for this, because no pirates say, rho squared sine phi d rho d phi d theta. That's not a thing. And yet, you still have that little correction factor. It's just this time, the role of the correction factor is being played by rho squared sine phi. Okay, that's the idea in 15.7. We'll have another video coming up where we do some practice problems. In the meantime, come to class on Monday with questions about these new coordinate systems, and we'll talk soon. See you next time.